Hello, it's Keith here, and this is episode 1 of my 6502 assembly tutorials. Now, if you're new to this channel, I previously did a series of 8 Z80 assembly tutorials, and I wanted to extend that and start teaching 6502. Now, I originally learned Z80 first, so these will compare and contrast 6502 to Z80 assembly. However, I'm assuming you know no assembly already, and I'm really aiming these for an absolute beginner at programming, so I'm hoping that even if you know no assembly, C or any other language, you should get some interest and experience using these tutorials, because I'm really hoping you can use them from an absolute no prior experience. So I'm going to show you today how we can use an assembler to compile quickly some code. I'm going to talk through how the code works. We're going to do some very simple samples, but most importantly, what I'm going to do is I'm going to provide, wherever possible, all of the source code, the tools, the emulators pre-configured for you to use within a Windows environment, so you can compile very simple examples very quickly and test those examples to see what they're doing and why, so that we can use assembly language, learn how the commands work and see the results with just a few commands, and we'll be able to get started really quickly. And because all of the tools I use are free or even open source, you should be able to download them for free, use them in whatever way you want. And although all of the tools I'm using are Windows based, they do all work very well on Windows XP, so even if you're using a Mac or a Linux machine, you should be able to use them through some kind of Windows emulation, a virtual machine. So hopefully you can get them working even if you are on a different system. Now, that said, the assembler I use is called VASM. It's a command line assembler, and it can be compiled to any system. So whether you're using Windows, Mac or Linux, you can get a native build of VASM. So you would just then need to provide your own emulators, but you could still use the assembly scripts that I'm providing. So you could compile the examples you're seeing today without a Windows machine at all if you so prefer. I'm just recommending Windows because it's my main operating system that I'm most experienced in, so I can provide very easy to use tools for Windows. So let's see what we're going to be looking at. Now, if you go to my website, you can use this Get the Development Tools icon here, and you should be able to download a 7-zip file of the tools that I use for my assembly. Now, if you've seen my YouTube channel before, I've recently done a Grime 6502 series where I ported a small Z80 game called Grime Z80 to the 6502. So I've been working on this last week, and I'm now doing the 68,000 version, but we're going to have a look at the build environment I used for that, because that build environment is literally the basis for these tutorials. So what we have is we have a folder here that is basically what you will get from that 7-zip if you choose to download it. And we have a batch file here called sdrive.bat. Now, if we run this, it will create a virtual S drive on your machine. And so I will run that now. But it has actually created a T drive on my machine. And the reason for that is I already had a drive letter using S. So we are going to use T here. But it makes no difference at all to the way the tools work. The 6502 tools will use S, T or U. The Z80 tools will use Z, X or Y. And the X6000 tools will use X, Y or Z, I think it is. Anyway, so we now have a virtual drive and we have this tree structure, and you should be able to see it's fairly logical. We have a variety of folders here. We have build folders here. These are the code that's being assembled that will be executable. A release folder here. This is the finished code. An emulator folder, which is obviously the emulators. As I say, they are all free, the emulators I use. Source folders, which are the source files for the common modules that we'll be building on. And sources, which is the main source codes that we will be looking at in these tutorials. We also have a utilities folder, which is some tools, including a few that I've made myself here, that we will be using as well. As I say, if you don't want to use my tools, you're welcome to just use VASM and the source files. The source files will be available separately from these tools because they will be more frequently updated. But whatever way you want to do things, hopefully these tutorials will help you learn very quickly, very simple 6502 assembly. So, well, all of my assembly is done within Notepad++ these days, so let's start that up. So here we go. We have a Notepad++ window, and you'll see I've already pre-configured this with rather a special trick. If I press F6, the MPP exec script will execute, and we'll show this build script where I can select a destination computer using these short abbreviations and compile for that system. So let's just very simply, to start off showing you this, so if I go into the sources folder, and load up lesson 1, and I will just press F6 here and hit enter, and you can see I've just built for the Nintendo NES. Okay, so I'll just exit that NES emulator, press F6 again, change to the PC Engine. I've just built the same program for the PC Engine, and we'll just do another one. There's the Super Nintendo. So we've run the same program on already 3 systems, and I could go through the list. It will run on every single one. We will learn how this works. The trick is basically that I've written headers and footers and various little driver code that will handle the complexities of each system and kind of build them down to a common level. Now, I'm aware that there's many other toolkits that will do this for you, but I think the unique thing that I can offer to you as a follower of my series is we're not just going to use this to write programs using my toolkit. We're actually going to learn how to write the toolkit. So if you don't like my toolkit, you can learn how it works and then replace it, make your own better one, or whatever you want. The reason I'm using the toolkit at this stage is because it allows us, whatever system you want to run on, you can use test code in seconds. I mean, all we've got here is 3 commands, and we can immediately run that on nearly a dozen systems. It's really great to be able to get you started this quickly. And just in case you don't believe me, I will just change this command to a 68 and run again, and you can see it's now showing 68. Well, what about if I change it to a 33? It shows as a 33. So I'm not tricking you in any way. This is a script that is immediately compiling to a hardware platform and then running on an emulator. This is really code on the screen going straight to the emulator. So let's have a quick look at how that works to some extent. Now, the magic all happens within the Utilities VASM folder. Now, if you look in this folder, you will see a wide variety of executables here that will be doing the actual compiling. There are all different versions for all different systems, not most of which we're not going to use. The important ones for us here are these ones at the top here. So let's just have a look at the Nintendo NES one. Now, this is the command that actually converts the source code into an executable file. In the case of the Nintendo NES, we have to build a .NES cartridge file, and it's a relatively simple format. We don't need to do too many tricks here. The assembly files are doing all of the building. Now, in some cases you would maybe see a few extra lines in here that would be maybe fixing up a checksum or attaching some other binary files to the header or the footer. As I've said, if you're using Windows, you hopefully won't need to worry about any of this, but I do want to explain it just in case you want to try and convert my scripts to run on Linux or something. So you can see here we're using this version of VASM here. We are enabling the check labels command. This makes sure that there are no return commands or anything on the far left that will be misinterpreted as labels. Common cause of bugs there. We're ignoring case sensitivity just to make our debugging a bit easier. We're defining a assembly. Now, it's something we're not really going to cover yet, but there's something called symbols. They're defined text values that have a numeric value, and I'm defining one as VASM, which is something I used to use to differentiate between VASM and WinApe as my assembler on the Z80. It's not something we need to worry about here. We're outputting a file called listing.txt, which is for debugging if we have any problems. Shouldn't need to worry about that though. We're outputting to a binary file, that's what this is saying, and the output is this file name here. Now, this is the important one here. We are defining another pre-configured symbol here called buildNES, and we're setting it to 1. Well, what does that mean? Well, this is how I am able to so quickly compile to so many different systems. You see, if I just go to the sources all folder here, and if I go to the header, you'll see here I'm checking which one we're compiling to and including alternate files depending on the destination system. But I know that's probably a little bit confusing for you, and I don't want to go into it in more detail than necessary now, so we're going to leave that at this point. We're going to come back to this kind of thing later. I just wanted to give you enough information in case you didn't want to use my scripts and you wanted to set things up on their own. If you didn't understand that explanation, just don't worry about it. Download the development tools on my website and the source files, and you should be able to do everything without worrying about that at all. So, depending on the platform we want to build to, we do need to have a definition, but as I say, if you're using my tools, you shouldn't need to worry about it. Now, let's have a look at the structure of our programs here. So, this example here is the first piece of code we're going to try. You can see there's a kind of template header here, which is going to at this stage be pretty much the standard for what we want to leave alone. And you've got a footer here, which is including various scripts that will help us along. So I'm suggesting you don't mess with those at this stage and just do your programming in the area in the middle. Let's talk about the 6502. Now the 6502 is very different to the Z80. The Z80 has a lot of different registers, but the 6502 essentially only has 3. So what are registers? Well, the registers are small bits of memory within the processor itself that are used for storing values temporarily without storing them back to memory. The 6502 only has 3 of these as their main registers, A, X and Y. Now A is the accumulator and X and Y are basically everything else. They're primarily offsets when we're writing or reading data to memory, or they are used as loop counters, but we can use them in a wide variety of ways, and we're really going to look at that at a later date. We're not particularly going to go into that today. I just want to get into the real basics of how the system works. But let's have a look at that example again. Now the first important thing to notice is that all of our commands are indented by one tab. If we put a command here, it would actually not function correctly. The far left of the screen is for something known as labels. Now we're not using any labels today apart from the one you'll see at the very bottom here, but it's important to notice you need to put a tab in before typing any extra commands, and you mustn't delete any of the tabs here, otherwise you'll get a warning or an error. So here's the first example here. Now we've got this jump to a command called monitor, which is a program I've written to show the status of the registers so that we can see what the system is currently doing. So we're just using this as a quick way of seeing what's going on in the processor. And then we've got a jump to star here. The assembler converts star to the current line, so we're jumping to the current line, which is an infinite loop. That just means the system stops. So we're just stopping the system as a very easy way of keeping things static. So what are we doing here? Well, LD stands for load. We're loading A with a value here, and we're loading in the value hexadecimal 33. Now, if you don't know what hexadecimal is, I suggest you sort of look that up. There's a separate video on my YouTube channel that does go into some detail about hexadecimal, but just as a quick summary, it's essentially base 16. Human beings have 10 fingers, so we count from 1 to 9 and then go up to 10. Well, hexadecimal goes from 1 to 15 before it goes up another digit. So let me just give you a demonstration of that. So if I type in 15 here in my decimal mode on this calculator and then convert it to hex, you see that goes to F. Well, that's a little bit odd maybe, but if we do +1 and go up to 16, it now goes to 10. Now, you probably think that's a bit weird, and you're correct, it is, but all I need you to understand at the moment is that hexadecimal and decimal are different things, and that hexadecimal is the kind of way that the computers tend to work better, and it's what the monitor is showing on screen. So that means we can do strange things here, like loading A with the hexadecimal value FF. And if we just run that, you'll see we're now showing an FF here, because I loaded in the hexadecimal FF there. So let's just have a look at these other two symbols here. We've got a dollar symbol and a hash symbol. Well, what do they mean? Well, the dollar symbol means hexadecimal. If I take it away and try and build again, I can't build because FF isn't a valid number, but 255 is. So if I build now, we still have FF. Well, why is that? Well, 255 is FF. If I change it to 254, we now have FE. So the dollar symbol meant hexadecimal. So if I put it back, I now can't build again because 254 isn't a value that's valid for a hexadecimal byte. So there we go. So the dollar means hexadecimal, and if we take it out, we're giving a decimal number. Well, the other symbol that might be interesting to you there is the hash symbol. What does that mean? Well, that means a fixed number. If we put that in, we are specifying a number to the LDA command to load into the accumulator. Now, if I take that number out, what actually happens is we're loading a memory address. Now, obviously, this isn't really what we're going to want to do at this stage, but we can, of course, do it. So now we've got value 55 here. This is not related to decimal 254 in any literal way. What's happened is we've loaded in the byte from memory address 254, and we're now showing that to the screen. So perfectly valid command, but possibly not what we want unless we know what's in memory address 254. So let's have another look at that with example 2 here. So here you can see we're loading in hexadecimal value 69 into the accumulator. This time we're also going to play with that X and Y register. We're using the load command to load in X to decimal 69. And we're also going to load in Y to memory address 69. So the accumulator will be set to hexadecimal 59, the X register will be set to decimal 69, and the Y register will be set to memory addresses 69's value. Once again, we're going to call the monitor, and then we're going to pause in an infinite loop. And this time, just for a change, let's build for the VIC-20. So here you can see the accumulator is set to hexadecimal 69 here. The X register is set to 45. Well, what does 45 mean? Well, let's have a look. 45 in hexadecimal is 69 in decimal. So you can see here that because we've missed out that dollar symbol there, we've passed a decimal value to the X register, and that's what's showing here. Now, memory address 69 clearly is 0 because that's what's showing in the Y register there. So this is how we can load values into our registers just by using LD for load and the letter for the register, either A, X or Y, because those are all the registers we have on the system that we can use to store values. Now, there are a few other tricks we can do here that will be less common but will be still very important. We can use a % symbol to use something called binary. Binary is how the computers work. They work in ones and zeros. A cluster of 4 ones or zeros make up a nibble, that's 4 digits, and one nibble is equal to one hexadecimal letter from 0 to F. And then 2 of those make up a byte. A bit confusing, I know, but as I say, I've done other tutorials on this if you want to see more at this stage. You can also do ASCII values by just putting a letter in quotes here, or even just one quote. And then, as I said before, a numeric value or a numeric value with a dollar at the start will be a memory address. So we will be loading from that memory address. If you've not figured it out yet, I'll tell you in advance, you will make a lot of mistakes forgetting that hash symbol and end up reading the wrong values from memory addresses when you meant to pass a fixed value. So I'll warn you that, just be careful of it. Now, there is another command we've had here, JSR. This stands for jump to subroutine. If you're familiar with Z80 assembly, it's called call on that system, but effectively we go and run a program, and then once that program's done we come back again and do the command directly below. So if I just put JSR monitor here a second time, you'll now see that the monitor has run twice because the first one executed showing at the top and then the second one executed showing just below. So the JSR command will allow us to do a task and then come back ready to do another task again. This is something we're going to go into in a later lesson. We're really just looking at the basics of mathematics at this stage, but I really want to not have any mysterious stuff that I'm not properly explaining to you. Now, if you're familiar with BASIC, then the JSR command is the equivalent of GoSub. Now, jumps are something else. Jumps don't come back, but the only jump we're doing here is an infinite loop. As I say, we're going to cover all of this in later lessons. Let's just try and stick to the mathematics today. So we want to do some mathematics now. So we've looked at how to load different values into the registers, but what about if we actually want to change those values by increasing them or decreasing them? Now this comes into something quite unusual about the 6502 that I do have to explain to you. The 6502 was based on the 6800 processor. The 6502 was a cost down version. They removed some of the functionality, and quite surprisingly one of the things they removed was the add command and the subtract command, which sounds quite absurd, but they did leave the add with carry command. It's a little bit confusing, but the add with carry command allows you to add a sort of remainder from a previous addition. I know that's frustrating and I don't really want to explain it at this stage, but all I want to explain at this stage is if we want to add to the A register, the accumulator, then what we need to do is do an ADC, but first of all we need to clear the carry with a CLC. So what I'd suggest you think about is imagine these two commands together are your add command, and then with the subtract command you have to do an SEC to set the carry and an SBC to subtract a value. I apologise, I know that's confusing, but that's the way it works, and it'll start to become more clear in the future. So as I say, at this stage, just think I want to add CLC, then ADC. I want to subtract SCC and then SBC. And CLC stands for clear carry, and ADC stands for add with carry, and SCC stands for set carry, and SBC means subtract with carry. This might surprise you if you're familiar with Z80, because the subtract command works backwards with 6502. We have to set the carry to not add any extra values. But as I say, if you don't understand that, just ignore it and just consider those two commands together to be a subtract command. So what are we doing here? Well, we're setting the accumulator to 15 here. We're then adding 1, and then we're subtracting 1, and we're showing the monitor at each stage. So let's fire that up on another system. Why don't we try the Commodore 64 this time? So a rather wide font, I apologise, but you can see here at the top the accumulator is 15, because just after this load hexadecimal 15 we called the monitor. Then we added 1 and called the monitor again. So you can see here that A is now 16. Then we subtracted 1 and run the monitor again. So you can see it's gone back down to 15 here, exactly as we expected. Well, what else can we do? Well, let's try something a bit more adventurous. Let's try putting in A0 here in hexadecimal. And let's run it this time on the BBC. So you can see here that the first value is 15 in hexadecimal. Then we added A0. Now 1 added to A becomes B, so the result is B5. Then we subtracted 1 in decimal, and so this became B4. And just to remind you again, if I take that hash out there, we will now be adding the value at memory address A0, and in this case we will be making a mistake, so who knows what will happen there. Well, it's actually gone down, which is a bit tricky, and it looks like probably the value 255 was at that memory address. A bit more technical than I wanted to go into there, but just warns of the perils of remember your hash symbols if you want to do fixed number values and not read from memory addresses. Now, whenever we're doing addition or subtraction, we can only do them on the A register, the accumulator. The X and Y register cannot do that kind of addition and subtraction, so we can't do that kind of thing to those registers directly. But what we can do is we can move values into the other registers from the accumulator or to the accumulator with other commands. So we're going to have a look at another example here. So we're going to load the A register here with hexadecimal 25, and then we're going to load the Y register with hexadecimal 34. And we're going to use two new commands here. TAX, which is transfer A to X, transferring the A register, the accumulator, to the X register. And then we're going to do TYA, which is transferring the Y register to the A register. Very straightforward. Now you can see them here. So let's see that in action. This time on the Apple II, which is alarmingly large. So what's happened here? Well, we loaded the accumulator with our 25 and our Y register with the 34 here, and then we ran the monitor. Then we transferred the A register, the 25, to the X register, which is now 25 here, as we would expect, and then we transferred the Y register to the A register here. Now we could even go further than this and do some more stuff. We could transfer the A register to the Y register and the A register to the X register and run it again. So now you can see we've made them all 34. I've done that just to show that there's a variety of commands. You can transfer A to X or X to A, Y to A or A to Y, but what you cannot do is this. You cannot do TXY or TYX. You can't do it, it won't work. But what you can do is you can transfer X to the accumulator and then transfer the accumulator to Y. So there's no way for X to go to Y or vice versa except via the accumulator. You see, the accumulator is your primary maths register on the 6502. Also on the Z80, of course, but as I say, with such a limited number of registers, you would maybe like to be able to do that and transfer between X and Y, but you can't do it in the same way you can't do most kinds of addition and subtraction on X and Y. There's a very limited way you can do it, but we'll go into that later. Okay, so we've learned how to set values into our registers. We've learned how to swap the values between the registers, but we haven't really learned how to do anything with those values once we've got them, except for show them on screen with that little monitor tool. So what can we do? Well, of course, we want to store values back to the memory for various reasons. Now, at the first stage, this is just going to be a test, but you would maybe want to save your lives back to your game once you'd decreased the player's lives, or maybe you'd want to calculate some pixels and draw them on the screen, which could actually become the bullets or the player sprites or things like that. And this is how we actually start to make something resembling a bit of fun. But for today, we're just going to keep things basic, and we're just going to store some fixed values to memory locations. So we're going to use another little tool that I've created called memdump. So what's this do? Well, the function memdump will take two values that follow it. One is a DW, that's a defined pair of bytes, and we're going to pass memory address 0 here. So we're going to dump the start of the system memory. And then this DB is a single byte, and it's the number of lines. Don't worry if you don't understand these. Just bear in mind you can change them and you can see different results with my test code here. So we need an infinite loop again, otherwise something strange will probably happen. And let's try on the Atari 800 and just see what happens. So you can see we've dumped memory address 0 here, and it's not fitted very well on the screen, which is rather unfortunate. Try the NES instead. So you can see we've dumped memory address 0 here, and we've dumped 3 lines of that memory address because there's a 3 here. And I can prove that to you if we just close that. We'll just change this to 10 and change this to 4 lines. So we've dumped memory address 10 here, or well, hexadecimal 10 that is, so 16, and there's now 4 lines here. So this is just a little quick debugging tool that I've programmed up for allowing us to see what's going on within the system without relying on debugging tools that are built into the emulators. Because when you're working on a lot of different systems or unknown emulators, that you tend to find that the debugging tools may not be there or may not be good enough. So I've come to rely on my own tools. So there we go. We've got this debugging tool that's going to show some bytes of the memory at memory address 0. And what we're going to do is we're going to try making some changes. So we've learned about the LDA command for loading the accumulator. Well, there's another command called STA, which is to store the accumulator. So let's have a look here. So the first command here is loading the accumulator. There's a hash here, which means it's a fixed value. There's a $, which means it's hexadecimal. And we're loading 11 into the accumulator. Then we're storing that into $0011. Now notice there's no hash here. That means we're storing it to memory address 11. And that will be in the same kind of area as we're dumping here. And that's why we're doing it. So let's execute that. So here's the before and here's the after. And you should notice here that there's an 11 here. Now each of these is 8 bytes, and 11 in hexadecimal is 17. So 8, 16, 17. And so you can see we've written to byte number 17 here in the value 11. And I can check that if I just change this value to EE here and run it again. You can see now that this byte has changed to 11. So it's definitely the value we've loaded into the accumulator here and then stored back from the accumulator here. So you can see that that is working. Of course, there's no need to just stop there. So we're going to load hexadecimal 11 into memory address 11. We're then going to load hexadecimal 22 into the accumulator and store that into memory address 12. Now what we're going to do is we're going to load the accumulator with 33. We're now going to do something a bit clever. Now you've probably realized that with just an accumulator in X and Y to store values into, we're going to be a little bit stuck. So what we can do is we can use bits of the system memory as extra places to temporarily store things, and that's what we're going to do here. We're going to clear the carry because we want to do some addition, and then we're going to add the memory address hexadecimal 11, which of course we've just primed with the value hexadecimal 11. We're then going to add with carry the memory address hexadecimal 12, which we've loaded with hexadecimal 22. And we're going to store the result at memory address 13. So let's see what happens here. So you can see here that the hexadecimal 11 we stored here has been stored, and then the hexadecimal 22 is here, and then we've got 33 here, plus 22, plus 11, and that in hexadecimal is 66. So you can see that was stored back there. Now we're doing ADC here for add with carry, but you could of course do subtract with carry as well. You could just change these to SBC, but of course you do need to do an SEC here for set carry, because when we do a subtraction we want to set the carry to make sure nothing else is added by accident. And then if we run it again, you see here we've got 11 and here we've got 22. So at this point we had 33. We then added the 11 here, which made 44, but then we subtracted the 22, and so we're back down to 22, which is why this is stored here. Now I said subtract with carry and add with carry could only be done to the accumulator, but fortunately the store command is available for X and Y as well. So if we just do LDX with 1,3 and LDY with 3,1, and then we do STX for store X, and we will store that at hexadecimal 0014, memory address of course, and then STY with hexadecimal 15, and we run this, you can see we were able to store that 13 and that 31 from the X register directly to memory addresses 14 and 15 without using the accumulator. So LDX and LDY and STX and STY are the loading and storing commands for the X and Y register. So although we can't do addition and subtraction directly to X and Y, we can store and set them very easily directly from memory or fixed values. So there we go. We've looked today at the basics of registers, how to transfer values into them, how to transfer values between them, and how to store those values back to memory. We're going to discuss all of this a lot more in the future, but I wanted to keep the introduction lesson today fairly simple to get people started. I will, however, warn you that if you're used to Z80, the first 512 bytes of the 6502 is very special. The first 256 bytes of the 6502 are something special called the 0 page. It's used as a sort of temporary store. Then the stack pointer, which is something you may know if you're familiar with Z80, that is fixed between hexadecimal 100 and 1FF, so the following 256 bytes. So that's just something to warn you. If you do start playing around writing different areas of memory, you might want to steer clear of that hexadecimal 100 to 1FF range, because you might crash your program. But anyway, it should be okay anyway. I just wanted to give you a very quick warning of that. But that's going to be stuff we're going to look at in the future. Now, one thing I will say, if you're not using my tutorials at all, you may find you have problems because the operating system will be using certain areas of memory at all times, and the examples I've given you today are kind of in a clinical environment where I'm controlling things like the system operating system, the firmware, to stop it messing things up with these tutorials. So again, if you're doing things yourself, feel free, I totally encourage you, but I'm showing you stuff I know works, and if you're doing other stuff, you may find it doesn't work as well. So there we go. That's all I really wanted to cover for today's lesson, just enough to get you started and feel like you'd made some ground in 6502. If you want to rush ahead, please check out my website, because I do have a lot of introductory content that goes into much more detail of this kind of thing, but I'm hoping to be able to go through it all in stages at a much sort of slower pace and really give you all of the depth on it, rather than kind of rushing through things and not really giving you a chance to understand it. But as I say, if you want to rush ahead, please look at my website. If you want to see more 6502 straight away, check out Grime 6502, my programming project, where I made a game in 7 days. But next time we're going to be looking into more detail about how memory works with the 6502, because the 6502 has a lot of special tricks that the Z80 doesn't have, and that's how it gets around its lack of registers. I hope you'll join me for that. So if you enjoyed this video, please like and subscribe it. Anyway, thanks for watching today, and goodbye.